Spectroscopy. Today we are going to see infrared spectroscopy as per the Pharmacy Council of India syllabus. For the subject BP701T, Instrumental Method of Analysis, which is for semester 7 of final year B.Pharm. In this video, we will see the theoretical aspects of IR spectroscopy. First, we will see the introduction, and we will see the fundamental modes of vibrations in polyatomic molecules, IR spectrum. We will see various regions in IR spectrum and factors affecting the vibrations. Now, in spectroscopy, transitions between different energy levels within the atoms and molecules are recorded to give useful information on chemical structure. Molecule is perturbed by these energy probes, and molecular responses are recorded as the spectra. Different spectroscopies have different mechanisms. For example, UV, you see the transition of electrons from ground state to excited state. While in IR, it is the vibrations of the bonds which help you to recognize the functional groups. In NMR, it is the resonance, or it is a spinning of the nuclei. They resonate with the applied magnetic field, so it gives you the idea about the environment of proton environment or nitrogen environment or carbon environment, depending on which NMR we are studying. And actually in mass spectroscopy, it is a fragmentation of the molecule and in a specific fashion, and if we study the fragmentation pattern of that spectra, we can deduce the exact structure of the molecule. So for an excitation process, a molecule absorbs only a discrete amount of energy at a particular frequency, and that too characteristic of functional groups and its molecular arrangement or architecture. Like I told you, in spectroscopy the range of energy is very large and spans all along the electromagnetic spectrum. As I just told, this is again briefed. UV visible is chiefly caused by absorption in the UV visible region is chiefly caused by electronic excitation. In IR, it is due to molecular vibrations of various kinds, while in NMR, it is owing to nuclear spin transitions. So before we move to anything, we should understand few things. That spectroscopy is the study of interaction of matter with electromagnetic spectrum. Electromagnetic radiation displays properties of both particles and waves. The particle component is called as a photon, and the energy component of this photon is proportional to the frequency of the energy of the radiation, where h is Planck's constant and nu is the frequency in hertz. So the equation comes energy is equal to a constant h into nu. The term photon means it's a very small massless particle and contains a small wave packet of electromagnetic radiation. Now, because the speed of light is constant, the frequency nu, that is number of cycles of waves per second can complete in the same time, must be inversely proportional to how long the oscillation is there or wavelength is there. So nu is c upon pi. So there is an inverse proportionality between the frequency and wavelength. Means longer the wavelength, shorter the frequency, and shorter the wavelength, higher is the frequency. Means higher energy radiation has higher frequency but short wavelength. And combining these two equations, for example, E is equal to h nu and B is equal to c upon lambda, we can deduce final equation. E is equal to Planck's constant into frequency, which is inversely proportional to lambda. Again Planck constant comes and the constant c is equal to 3 into 10 raised to 10 centimeters per second. So that is the velocity or speed of the light. And when we talk about the oscillation of the wave, it has got certain height, and that is described by the amplitude. And because atomic particles in matter also exhibit wave and particle properties, electromagnetic radiation can interact with the matter in both the ways, that is particle to particle collision, where friction or energy is lost as heat due to friction and movement. And as I told you, it is also the waves or the radiation. So coupling the wave property of the radiation matches the wave property of the particle, and the coupled to the next higher quantum of mechanical energy level. To summarize these relationships, therefore, again we come back, that is lambda into frequency is the velocity of light, or in other words, lambda is inversely proportional to the frequency of the radiation. Energy is Planck's constant into the frequency of radiation. That is, energy is directly proportional to frequency, while energy is inversely proportional to lambda. And this is lambda, this is amplitude, and this is the wave function. So if we see the electromagnetic spectrum, which can be expressed in the terms of frequency, you will see the frequency goes on increasing this side, or it can be inversely expressed in terms of lambda in nanometers, and you can see that it goes on decreasing continuously from this side. So shorter the wavelength corresponds to higher the frequency and corresponds to higher the energy, because energy is also increasing. So we understand these equations, and these equations are here expressed pictorially. Now in short, this is the electromagnetic spectrum, and at the shorter wavelength or at higher frequency, you have got the most intense energy, that is the gamma rays, or the where nuclear excitation takes place. This is followed by the X-rays, where core electron excitation takes place. So X-ray crystallographies can be performed at this region. Then comes the UV, that is electronic excitation from pi transition or N star transitions. In between comes the UV visible region. Then comes the IR, which is just able to vibrate the molecules or their bonds. Still weaker is the microwave wave, that is the molecular rotation, and still is the radio frequency, wherein nuclear magnetic resonance or NMR or even MRI are performed. So now we are talking about IR here, and this again has been nicely expanded to explain the electromagnetic spectrum in more details. As we saw, we have got cosmic rays, gamma rays, X-rays. So these are all for nuclear transitions. X-rays are again higher in energy than the UV. And here comes the UV. And then here comes the near UV. This is the visible region. And then this is the near IR, this part. This is IR. This is far IR, this is microwave, and these are the radio waves at different frequencies. And we can see what happens here. Here is the radio, actually radio frequencies we can hear. This is the NMR FM radio region. These are the molecular rotations, and that is all microwaves operate at this place, and these are the molecular vibrations that I am talking about, IR. And these are the electronic transitions, somewhere 400 to 800 nanometers. That is visible. And then 400 onwards to 200, we are going to the shorter, means higher energy, that is a UV, and this is a vacuum UV, which is even still shorter. And so here this is the range given of the near infrared, that is something around 4000 centimeter inverse to 12,500. This is mid infrared, which is 200 to 4000. This is our mid infrared we are going to talk. This is far infrared 10 to 200, and most used is this region. So this region we are using most, mid infrared. Now here it is given radiation and outcome, radio wave, nuclear spin flips, okay, microwave molecular rotation, infrared bond vibration, visible electronic excitation, UV also electronic excitation, X-ray molecular ionization, and gamma ray is bond cleavage. Now, so we saw the infrared region, we probed it much details and we understood what is near infrared, that is this region, mid infrared, that is the thing which we are interested, and far infrared. And so again in the electromagnetic spectrum you got a near infrared, you got mid infrared, and you got far infrared. It is the fastest and cheapest of the spectroscopic techniques used by organic chemists to get information about functional groups, and it's mostly qualitative. Simply measurement of the absorption of IR frequencies when a sample is placed in the path of the IR radiation. Samples can be solids, liquids, or gases and can be measured in solution. Either you can make solution in some solvent like chloroform, which should be moisture free, or you can make a suspension in Nujol mull or paraffin, which is dried with sodium, or you can use KBr or NABr as a solid phase, wherein you can mix the compound and you can compress it under a high pressure of 12 tons to a transparent thin pellet. And nowadays you don't need to make solution or even make a pellet, you can directly put the neat sample and it is placed in the path of the IR beam, and this is called as ATR. The spectra thus obtained are just in few minutes of partially purified material. You don't need extremely pure material because you are only interested in understanding the functional group, what you are looking for. And many times it is for characterization of the compound, it is also for identification of the compound by comparing it with the standard compound, or it is also to monitor a reaction, like during the reaction a functional group is getting converted to some other functional group. You will see the change in the starting material IR and you will see the change in the reaction mixture, and final compound you will see a different group like cyano get converted to amino. So suddenly you will see that 2200 centimeter peak is vanishing and you are getting a new peak between 3200 to 3400, either as a doublet. So this it's very simple tool. In minutes you can take an IR. Only thing you have to follow for very anhydrous conditions because all the optics is made of KBr. Now the covalent bonds of the molecule behave as tiny springs, and they don't remain in a fixed position. They continuously are active. They keep on vibrating back and forth. And when internal vibration energy of a molecule matches with the incident energy of the applied IR radiation, molecule attains resonance. When these two energies, like the incident IR energy and the internal energy, both match and they resonate, molecule is able to absorb the IR radiation. And after absorbing this IR radiation, the molecule gets excited from the ground or lower level to higher vibrational level, and this leads to increase in the amplitude of its regular bond vibrations to slightly higher ones, and this is recorded in the form of a spectrum. The spectroscopic process, the quantum mechanical energy levels observed in IR spectroscopy are those of molecular vibrations, and we perceive this vibration as heat. When we say a covalent bond between two atoms is of a certain length, we are citing an average because bond behaves as if it were a vibrating spring. So actually we are always telling the when we say bond length is this 1.33 Armstrongs, it is many times a calculation of the average because sometimes it may stretch to 1.45 also and sometimes it may compress to 1.3 also, but so it is continuously coming going away and coming again near, and so in this figure you can see it is compressing completely going forth and back, and it is compressing and it is expanding. So an average length is, and that is what we call it as a bond length. So all bond lengths which are expressed in particular Armstrongs are actually near to average bond length. This is a simple diatomic molecule, and it's very, you can see the vibrations, and this is just approximating a spring. So, for calculation purpose, like we have quantum mechanics and we have molecular mechanics, and molecular mechanics are very easy, but they are approximate. So we visualize the atoms as balls and the bonds as springs. So some basic concepts still we will see that in IR spectroscopy, we observe the vibrations of bonds, and this vibration actually lead to give us a knowledge about what is which function groups are there, because these are characteristic vibrations. In IR spectroscopy, the photon energy level that are assessed are those that involve molecular vibrations, and these molecular vibrations are corresponding to certain energy levels. So when a molecular vibration involves a change in the dipole moment, then that vibration is active in the air and can be observed. Only those molecular vibrations elicit or bring about some change in the dipole moment of the molecule. They are observable, recordable, and they are called as active IR vibrations. And vibrations that do not involve a change in dipole moment are inactive in the IR and are not seen in the IR spectrum at all. So these vibrations or rotations in the molecule are quantized in the form of either the wavelength or in the form of frequency, which are expressed correspondingly in nanometers or micrometers, sorry, wavelengths, and this what you can say the vibrations into centimeter inverse, that is frequency. Most molecules contain permanent electrical dipole moments due to imbalance in the charge and the shape of the molecules. Molecular vibrations and rotations result in fluctuating electric fields at frequency that varies with elemental and structural compositions. Infrared radiation has frequencies that correspond to oscillating electric fields in the molecules. And when the frequency of incoming infrared radiation matches with the frequency of at which electrical fields oscillate, radiation can be absorbed, and this is again shown very nicely in the next figure. So what is important here is when a molecular vibration involves a change in the dipole moment, then that is active and it is observed. But if it doesn't elicit any change in the dipole moment, it is IR inactive and it is not seen in the IR spectra. So if the vibrational molecules in transitions in a molecule are capable of changing its dipole moment, then the molecule is said to be IR active. Now dipole moment in symmetrical molecules, you don't get dipole moments like in ethylene or in H2 molecule or nitrogen molecule or chlorine molecule, because they exactly cancel each other and they are inactive. You don't see bands. But all functional groups are asymmetric, therefore they are detected by IR. So we have understood an important concept, that is electrical dipole moment, which is a measure of imbalance and separation of the positive and negative charges as two poles in the molecule. And in order for there to be a permanent dipole moment, there must be a permanent net imbalance of charge. So you should have one part of the molecule which is having more concentration of electrons and other is electron deficient. So you should get partial negative and positive charges. Like you can see in the molecule of HCl, simple HCl, see you can, the central electron pair has been more shifted towards the electronegative chlorine, and this hydrogen has been deficient, so it has acquired a positive partial delta positive charge, and this is delta negative charge. Water molecule also, you have water. Oxygen is very much electronegative than the simple hydrogen, so the hydrogens are deficient. They exist like protons, while oxygen is negatively charged. The molecule has more than two atoms. Both shape and bond polarity determine the overall molecular polarity. So the IR spectroscopic process is when a covalent bond oscillates due to the oscillation of the dipole of that molecule, a varying electromagnetic field is produced. So the greater the dipole moment change through the vibration, more intense is the electromagnetic field that is generated. Now, this spectroscopic process, when a wave of infrared light encounters this oscillating electromagnetic field generated by the inherent vibrations of the molecule, um, if both the waves couple, that is, if you put a sample in the incident infrared radiation, the molecule has its own inherent vibrations. So some field is produced, electromagnetic, and the IR radiation is also falling on that, and when both of the frequencies match, then they couple, and the couple wave now vibrates with a double amplitude, and they sum up. So here is your inherent, what you say, the sample inherent vibrations so taking place. It is generating this thing, what you say, a field of its own. And now on this is falling the infrared radiation. So this and this is getting added up, and the amplitude of the coupled wave is doubled. So they sum up. What is the vibration in a molecule? Any change in the shape of the molecule, stretching of bonds, bending of bonds, or internal rotation around single bonds. Can a vibration change the dipole moment of a molecule? Yeah, asymmetrical stretching, bending, and internal rotation change the dipole moment of the molecule. And such asymmetric stretching, bending vibrations are IR active, while symmetrical stretching, bending does not change the dipole moment of a molecule, so they are not IR active. There must be a change in the dipole moment during a vibrational cycle. Homonuclear diatomic molecules will have no IR spectrum. So we have two classes of compounds. This is diatomic symmetrical homonuclear diatomic molecules. There is no dipole, that is O2, H2, Cl2, they are IR inactive. While compounds which have a very clear cut electronegativity difference like HCl or H2O or NO, they will be definitely having a dipole moments. They are IR active. Now we assume in the quantum mechanics, molecules as a set of balls and the bonds and springs which are continuously vibrating, and therefore these balls are attached to the springs, and they are also moving front and back. So for calculating their vibrating frequency, that how many times they are vibrating in a given unit time, we use the Hooke's law, which is used for the vibration of spring or the elasticity of the spring, and which correlates the frequency of vibration with bond strength and atomic masses, and is given by the Hooke's law equation. Frequency is equal to 1 to pi c, which is a constant, into the square root of k upon mu, and k is the what you can say, force constant, and or we can call it as bond strength, and mu is the what you can say, atomic masses, or reduced mass it is called. So where nu is the frequency, c is the velocity of the radiation, pi is a constant, k is a force constant, Mu is if the atom is containing two atoms, if the molecule is containing two atoms, M1, M2, so it is a product divided by sum of these atoms, atomic masses. So therefore, if K increases, frequency increases. That is, if the bond strength of the force constant increases, which is on the numerator, your frequency increases. But if the mass product increases, frequency decreases. So if your molecule has bulkier atoms, your denominator will increase. And therefore, if you see, compared to H, carbon is heavier, compared to carbon, oxygen is heavier, compared to oxygen, Cl is heavier, compared to Cl, Br is heavier, and therefore the frequencies go on decreasing. Because heavier atoms will not vibrate that frequently as the lighter, or CH will vibrate like anything. Now let us do some calculations of CC bond vibrating frequency in IR for a CC double bond. So you have the force constant is given for CC double bond is 10 into 10 raised to 5 dynes per centimeter, and frequency by the we can calculate by the equation 4.12 into K mu, K upon mu. So you have the atomic weight 12. So 12 into 12 upon 12 plus 12, so it becomes 6. So you have to take 4.12 into square root of 10 into 10 raised to 5 divided by 6. So 1682 centimeter inverse, which should be the calculated frequency of a CC double bond, and actually experimentally it is found somewhere plus minus 1650. Similarly, we can see for CH. For CH, again, the force constant is 5 into 10 raised to 5 dynes per centimeter. Masses, of course, have been decreased because hydrogen is only 1, so the product comes 0.923. So you can see, though this has decreased, this has substantially decreased, and therefore you get the calculated value much higher than the C double bond C. And experimental is quite near to it. If you take C deuterium, then the force constant is more or less the same, only there is a difference in the mass, and mass is increased by 1 of instead of 1 of the hydrogen, it's deuterium. So the denominator is slightly increased and this is slightly reduced now. So it is in between these two, and the calculated is quite matching to it observed. So what wavelength of electromagnetic radiation is involved in causing vibrations in a molecule? So the wavelengths are between 2500 to 15,000 centimeter inverse, or 2.5 to 15 micro more. Or you can say even lower than that. You can say it starts from 600 centimeter inverse up to 15,000. For a vibration at 4111 centimeter inverse, that is a stretching vibration of an H2 molecule, how many vibrations can occur in a second? So 120 into 10 raised to 12 vibrations per second, or a vibration every 8 into 10 raised to minus 15 second. So this is too much. That is 120 trillion vibrations per second. That is too much. That is quite something. That's great, really, yeah. The number of possible vibrations within a molecule is, for a non-linear molecule, is 3n minus 6, and linear molecule is 3n minus 5. Now let us see what are the these figures, what are they and how they are calculated. So for that we have to come to the fundamental vibrations, that is, these are the real vibrations occurring by absorbing IR radiation in a molecule. Others are additional vibrations or weaker vibrations or overtones, etc. So the number of fundamental vibration bands is related to the degree of freedom in a molecule, and the number of degree of freedom is equal to the sum of coordinates necessary to locate all molecules of atoms of a molecule in space, and each atom has 3 degrees of freedom corresponding to the x, y, z coordinates, which are perpendicular to each other. And we generally always give xyz coordinates to show the position of any atom in the space. In a polyatomic molecule containing n atoms, you have 3n degree of freedoms. Now the molecule will have basically 3 types of motions: translational motions along the x-axis, rotational motions around the y-axis, and then vibrations around the z-axis. 3 coordinates indicate the translation motions across the x, y, z axis, and while the 3 are required for describing the rotational motion also according to x, y, z axis. So degrees of freedom is so therefore the fundamental vibration observed will be degree of freedom minus bands due to translation motions and bands purely due to vibrations. Bands due to translation motions are 3, and bands due to vibrations, that is stretching and bending, can be 2 or 3. For linear molecule they may be 2, for non-linear molecule they may be 3. So 3n minus 3 plus 2, that is 3n minus 5, or 3n minus 3 plus 3, that is 3n minus 6. So translational, in linear molecules you have 3, non-linear molecules you have 3, rotational you have 2, in linear here you have 3. Total degree of freedoms are 3n. So vibrations or bands you will observe 3n minus this 5 bands, and for non-linear you will find 3n minus this 6 bands. So methane is a non-linear molecule, ethane is a non-linear molecule, carbon dioxide is a linear molecule. So for methane and ethane you will use the formula of the 3n minus 6. So in methane you have CH4, that is 5 atoms. So n is 5. 15 minus 6, 9. There are 9 fundamental vibrations. In ethane you have 8 atoms, so 3 into 8, that is 3n. So 24 minus 6, so 18 fundamental vibrations. In carbon dioxide, which is a linear molecule, you have 3 atoms, so 3 into 3, 9 minus 5, that is 4 fundamental vibrations. So let us see the carbon dioxide molecule, and you have 4 fundamental vibrations. This is linear molecule, just straight molecule along one plane with 180-degree angle. So which are these 4 fundamental? One is the symmetric stage, another is the asymmetric stage, that is this is symmetrically stretching in both directions, this is asymmetrically stretching only in one direction, this is scissoring, that is carbon is coming this side and oxygens are going inside the plane, and this is opposite scissoring, that is out of the plane. So you get 2 more bands. So these 2 bending vibrations, you can say scissoring, and the stretching are symmetrical and asymmetrical. So 4 bands, and that is also through calculation. So these which bands? These bands they are described. You get another non-linear molecule, water, which has got a dipole moment because the electron structure of oxygen atom in water molecule makes it non-linear. And so you use the formula of non-linear 3n minus 6. So water has 3, n is equal to 3, 3 into 3, 9, 9 minus 6, 3 different fundamental vibrations. So one is a symmetric stage, another is an asymmetric stage, and the third is a scissoring. Besides fundamental vibrations, sometimes the molecule absorb extra energy After moving to the first excited stage, they may further absorb a more higher energy and move to a higher stage, that is second, third, or fourth level. And due to this, it exhibits more bands in its spectrum, which are called as overtones. And most of the overtones are found in the near infrared region beyond 4000 centimeter inverse. So they are not much significant for our purpose, because we are going to operate between 600 to 4000 only, that is mid infrared region. So, but there are certain fundamental vibrations, and sometimes they act as a confirmatory test to confirm. Like for carbonyl vibrations, all carbonyl groups come around 1700 plus minus. Amide is 1650, ester is 1750, but they will give a small overtone at 3400. So when the molecule is in the lowest vibrational state, it is excited to the second vibrational. The energy needed is almost twice that is required for first vibrational level. It is not exactly twice, since higher levels are closer to each other, and it occurs when a single photon is precisely the correct energy to excite two vibrations at once, and these are called as combination bands. Now we will see last what are the factors which affect the vibrational frequency. So there are coupled vibrations, Fermi resonance, electronic effects, ring strain, field effect, and hydrogen bonding. So coupled interactions, we have say they take place between bonds vibrating through common atom, which are bonds of common atom vibrating with similar frequency. And when these atoms or these bonds come nearly close to the molecule, and coupling takes place when both fundamental vibrations or a fundamental vibration may couple with the overtone of same other vibration. We saw what are fundamental and what are overtones. So the latter, that is fundamental vibrations when coupled with overtone, this phenomena is called as Fermi resonance. Now let us consider a methyl group which is attached to benzene to give toluene. So you have three CH bonds to the toluene methyl group, and this toluene carbon is attached to these three hydrogens which are similar, and it is also attached to the benzene carbon. So you imagine the flat benzene ring, and this is a hanging group outside benzene ring. Now these CH bonds are quite flexible, quite light, and they are vibrating a lot. We have seen how many they are vibrating in terms of trillions per second. So when they are vibrating, there are many times chances that these are coming near each other, and not only near each other, along with the methyl group, they are also coming near the benzene ring. And when such things happen, the fundamental vibrations of the molecule uh, and these overtones, they couple to give Fermi resonance, and you get symmetric and asymmetric stretching vibrations. Asymmetric stretching occurs at higher frequency than symmetric stretching. No coupling is seen between groups separated by two or more atoms. So they need to be, fundamental thing is that there should be no separation or spacer between the substituent and the main molecule. And essentially these bonds should be on the same atom. One atom should be common. Then only it can come in close vicinity and they can resonate and produce Fermi resonance. Here I have given you an example of benzoyl chloride, and the two bands of the carbonyl region occur at 1719, 1745. The major band is the actual fundamental vibration, asymmetric stretching of the carbonyl group, but a small shoulder at comes Um, and this small shoulder at 1745 is a Fermi resonance. So this is a fundamental vibration, this is an extra band, and that we will get as a doublet, and this phenomena will be called as a Fermi resonance. And as I told you that symmetrical and asymmetrical come at a higher frequency. So methyl CH symmetrical and asymmetrical, anhydride also symmetrical and asymmetrical. In all amino, in nitro, all cases they are at higher side. Hydrogen bonding, stronger the hydrogen bonding, lower the frequency. Intramolecular and intermolecular hydrogen bonding is there. Intermolecular is between two different molecules. They generally lead to a broad band, and they are depending on the concentration. If the molecule is diluted and a less concentrated solution is made, then this intramolecular hydrogen bonding diminishes. Intramolecular gives sharp peaks, and here we can see this OH bond which is free sharp. This OH bond is free sharp, while this is broad. So this is intermolecular bonded, this is intramolecularly bonded. We have electronic effects also. First is inductive effect. If you go on increasing alkyl groups, they increase the length of the molecule, they decrease the bond strength, they decrease the force constant, they also decrease the vibrational energy. And here I have taken an example of formaldehyde, and if I replace one H with a CH3 group, that is an alkyl group, I will see that my vibration has reduced little bit frequency. If I remove this H also, it will further reduce. So these are all electron donating alkyl groups, that is plus I. But if I have a substituent of electronegative atoms, that is minus I, this phenomena will reverse. The bond strength will increase, force constant will increase, and therefore the vibrational frequency also increase. And so in acetone, if I replace one hydrogen with chlorine, I find the frequency going high, and if I replace it with two chlorines, I find it still higher. There are also feed effects and mesomeric effects due to lone pair of electrons, and this conjugation of the lone pairs with the main molecule conjugated system lowers the absorption. So we still continue with the factors affecting the vibrational frequency. Ring strain moves peak to right, that is decrease the frequency. Like you have got cycloheptene 1650, cyclohexene is 1646, cyclopentene is 1611, cyclobutene is 1566, and this is an exception. So why this consistently decrease? Because smaller the rings, there is more ring strain, and therefore there is a reduction in frequency. Substitution increases, that is if you put substituents on this, particularly methyl groups, they will increase with one methyl group, it increases with two methyl, and so in these cases. Conjugation decreases the frequency. That is, if you have phenyl ring and with a conjugated exocyclic double bond, frequency decreases. And here we have shown that this carbonyl group is conjugated. But if I put a spacer here, the frequency increases. I am breaking the resonance. Resonance is decreasing actually. And it decreases by 20 to 40 centimeter inverse. Here I have taken, this is all in a conjugated system. This resonance is very much there, and if I put a substituent which is able to conjugate and be a part of the resonating system, it will further reduce. But if it is breaking the resonance, that I can see there is no charge on the atom, it is not taking part in resonance, then I have compared here amino with nitro, and this has very much, amino has been very much part, even it has acquired a charge, and there is a good charge separation, so it is a strong resonance contributor, while this nitro has broken the resonance. Fine, this nitro has broken the resonance. My carbonyl oxygen is no longer bearing any charge, and it's not a part of the resonance system, and therefore I can see that this has got a higher frequency. Inductive effects are usually small unless coupled with a resonance contributor. These are the inductive, these act through inductive effect. They come in between. So conjugation lowers the absorption in this pair. This conjugation has lowered the absorption. In this pair, this conjugation has lowered. This is broken here due to spacer. Here there is a conjugation. So theoretically it should have been this much, but it has gone down. Electron withdrawing groups are increasing, while electron donating are decreasing. Steric effects, if you put a alkyl group which is creating a steric hindrance, these are, as long as this system is there, they are in one plane, but by putting this is thrown out of the plane, and resonance is broken, so this absorbs at higher. Same strain effects we have seen already, and we will see hydrogen bonding. Hydrogen bonding causes broadening in the band due to creation of continuum of band energy associated with it. In solution phase, these effects are very much apparent. In gas phase, they disappear, or also steric effects also disappear. Bands become sharper. Now this is 1-butanol, the OH is quite sharp. Steric influence to H bonding, you put diethyl you put around this, in the vicinity of this OH, you put very bulky steric groups. And it is still more sharper. It doesn't allow it to be in the same plane to resonate or donate electrons. Hydrogen bond can interact with other functional groups to lower their frequencies. So, friends, next time we will see I will show you the symmetrical vibrations, how they appear, asymmetrical vibrations, bending vibrations, scissoring, rocking, and wagging and twisting. But these are the stretching vibrations. You can see both are going symmetrical. This is asymmetrical. This is scissor. This is rocking. This is twisting and wagging. But this is the best figure. This is symmetrical. This is asymmetrical. This is scissoring. This is twisting. This is rocking. This is wagging. So we saw the relationships of electromagnetic radiations. We saw the molecular vibrations, the spectroscopic process of coupling, role of the dipole moment, Hooke's law and four constant and atomic masses, fundamental vibrations, type of vibrations just now we saw, and then we also saw, we will now, next time we will see IR spectrum and its various, what is an IR spectrum, what is x-axis, what is y-axis. You will see 9 different points to describe it, how IR groups are analyzed in 5 different steps, what are the 5 zones for characteristic staging vibrations, what are group frequencies, and most importantly, what is fingerprint region. So thank you very much for your patient listening.